So again, we talked about the very definition of work, saying that work is done when energy is used. And the most basic definition of energy is simply the ability to do work. So they go hand in hand. I can't have one without the other. So when we talk about types of energy, while we will loop in work more specifically later, we want to keep in mind that there is a connection, right? Their very definitions don't exist without the other term. The definition of work includes energy. Definition of energy includes work. So we're going to start with kinetic energy. Right, and just like kinematics is the study of the motion of objects, kinetic energy is energy of an object in motion. And if an object is in motion, is that object doing work?
Yes.
Yes. So we can also think of it as the energy doing the work. So how would I know if an object is in motion? What value or variable would it have? In terms of our kinematics motion variables, it has to have what?
Velocity.
Good, some amount of velocity. It has to be moving. Velocity is our measurement of motion. So kinetic energy, K, and on your formula sheets it does say K, not KE. You'll see KE in older textbooks, but AP none of the variables have more than one letter. There's like a letter and a subscript. So this is just K. Is equal to 1/2 the mass of the object times its velocity squared. Mass, as always, in kilograms. Velocity in meters per second. Energy of all kinds is measured in joules. And what other variable that we just learned about is also measured in joules? What do we do on Tuesday? Power's like a light bulb. Work. So note that work is also measured in joules. So energy and work share the exact same unit. We measure them in the same thing, which if we go back to our definitions, hopefully should make sense. Since they directly relate to each other, I can't do one or have one without the other one. It would make sense that we can sort of equate them through a common unit. So for kinetic energy, often we'll see proportional reasoning questions, which hopefully we're pretty comfortable with. What's the biggest thing that you would need to watch out for if you were doing proportional reasoning with kinetic energy? What in that formula is going to be something that you need to make sure you don't forget? Squared. So keep that in mind. So we'll do a quick practice. If both the mass and velocity of the object were doubled, what would happen to its kinetic energy? How much more energy?
8 times.
Good. So if mass and velocity double, 8 times the kinetic energy. So in terms of relationships, right, mass is directly proportional. So doubling the mass is going to give you 2 times the kinetic energy. But kinetic energy is proportional to velocity squared. So doubling the velocity would be 2 squared. So 2 times the velocity squared will give us 4 times the kinetic energy, and 2 times 4 gives us 8. Do I care about the 1/2 if I'm doing proportional reasoning? No, right? Constants don't matter with proportional reasoning because I'm going to do it to everything. So whether I double it, triple it, cut it in half, I'm still always multiplying that by 1/2. So it doesn't factor in with the proportional reasoning, only the exact variables themselves. So when an object does work, or it's doing work, it's using energy. So the next thing we're going to talk about is potential energy, the energy that it had to begin with so that it could be moving. And there are 2 types that we'll talk about. The first one is sort of the most basic version. So in general, potential energy, So if kinetic energy is the energy of an object in motion, potential energy is the stored energy. Right, it's not moving yet. In terms of work, where kinetic energy is the energy that's doing work, potential energy represents the work that could be done. It is the potential. So it could be predictive, right? If we think of energy in terms of calories, right? We're talking about mechanical energy, so it's not thermal or chemical or anything like that. If we were talking about chemical energy, if you consume X amount of calories, that determines how much exercise you can do. So if you eat 5,000 calories, right, that's your potential. That's potential energy expenditure later. But if you go to practice and you only practice for 20 minutes and then you leave, you still have some energy left over. So you can have both some kinetic energy, right? You've used up some of your stored energy, but sometimes you don't use it all. So you may have left over. So potential, again, represents that, what you could do. Not that all potential becomes kinetic, it just depends on the situation. So there are 2 types of potential energy that we'll focus on. The first is what's called gravitational potential energy. And for whatever reason, the symbol or the variable for potential energy is U. I think of it as untapped. I don't know if that's what they thought, but that's the only way I remember it. So it's not P, that's power. U, and then in this case, it would be U sub G for gravitational potential energy. And this is stored energy due to the object's position relative to the Earth or whatever other planet. All right, how far can it fall? And if I know how far it can fall, we learned in kinematics that we can figure out how fast it would go based on how long it falls and how far it accelerates. So gravitational potential, we're going to think of position. How high up? So the equation is typically written as mgh for height. On your formula sheet, though, they're writing it as potential energy equals mg delta y. Right, so height is a vertical displacement. This is a more generic way to think of vertical displacement. They felt like height might confuse people in a particular problem. Means the same thing though. So we still have the mass of the object in kilograms. Gravity is our negative 9.8 or 10 meters per second squared, so that's a constant. And then we have either height, or you can think of it as the vertical displacement. How far did it fall? Height tends to have people think about like the height of the first roller coaster hill behind Stone. Delta Y would be the change in height from top to bottom. One thing about gravitational potential energy is what we call non-path dependent. So just like in work, we don't care how fast. In terms of gravitational potential energy, we don't care how you get there. So you can take the elevator or you can take the stairs. If you're on the 5th floor, your potential energy is the same. So how you put it in has no bearing on how much you have, because the only variables we care about is the object itself, a constant due to the planet, and its height above Earth. It has nothing to do with the distance you covered to get there, right? So you could do it the easy way, you could do it the hard way. So when we think about it, what we're really saying is that the object could be here, right? So they're all at the same height. So these all have the same potential energy. But I could get to this one by walking up a hill. I could get to it by walking up the stairs. Or I could get to it by climbing up a wall. If the height is the same, then the object's energy will be the same. So thinking about the roller coaster behind you, or just in general, if I want a roller coaster to have more potential energy so that it can later have more kinetic energy, what do I do to the roller coaster, right? If we assume that the roller coaster cart's mass is the same, there are mass limits on the ride to begin with, so we aren't really able to change the overall mass in enough way that's going to make it significant. So how do you make a roller coaster faster?
Make it taller.
You increase the height. So if you think about the difference between the Mamba and a roller coaster in Camp Snoopy, the biggest difference is what? The height, right? The higher the hill, the faster you can go, because you're giving that object, that system, more potential energy that it could use to do work, which means to move the object, which ultimately gets measured in how fast it's moving it. And so the same works with lots of other things. If you want something to go really quickly, you're going to drop it from a higher height or put more in. So that's one way to give an object potential energy, mechanically speaking. The other way to give an object potential energy in terms of mechanics is through spring energy. Briefly, after our unit test about Hooke's law, we're going to do a quick review of that. So when we're talking about springs, we had Hooke's law, which said that spring force was equal to K times X. K being our spring constant, how tightly wound is the spring? Is it the spring inside of your clicky pen, or is it the spring in the suspension of your car, right? Very different springs. Your muscles function like springs as well. And what we knew about that was when I take that spring, right, there it is at rest. If I stretch it way out to here, right, this was its equilibrium point. That's where it wanted to be. I applied some very large amount of force on that spring to make it stretch. What is the spring doing in response? Pulling back, right? It wants to go here. So if I pulled on it with, let's say, 10 newtons of force, how much force is the spring going to respond with to pull itself back? 10 newtons of force. We had that equal and opposite idea of spring force. And the other thing to consider is that we stretch this spring a certain distance or a displacement. So did I do work on the spring?
No. Wait, which spring?
The one I stretched.
Oh, yes.
Yeah, right? I applied a force, it caused a displacement. Does the spring do work when it goes back?
Yes.
So did it have to have energy to do that?
Yes.
Yes, and that's what elastic or spring potential energy is. So we have elastic, sometimes called spring, potential energy. If we think about it as the spring, it's also a rubber band. If I take a rubber band and I stretch it back really, really far, and I hold it right next to Pat's face, am I hurting him right now?
No.
Do I have the potential to hurt his face? Yes. And where is that potential stored?
In the rubber band.
In the rubber band. The further back I pull the rubber band, the more it's going to hurt. So that's the same idea with spring potential energy. Just like bringing a roller coaster up really high gives it the potential to go really fast at the bottom of the hill, stretching that rubber band really far gives it the potential to snap back really far because of the force, right? I did this amount, it's going to do the exact opposite amount on the other end. And so that's where spring potential energy comes from. So since it is potential, it's still a U, but now it's US for spring. But I do want to make sure that we understand that springs and elastics are very similar. Your muscles utilize a lot of elastic energy. And when we talk about power and jumping especially, that's what we're doing. You're loading your muscles like a spring. So the equation for spring potential is 1/2 K, so going back to that spring constant, times X squared. So it looks very similar to like a weird version of kinetic energy, right? Instead of 1/2 mv squared, we have 1/2 kx squared. Just different variables. So K is your spring constant. Remember, this is a little k versus a big K. X is your displacement. And we're talking about how far it's either stretched or compressed, doesn't matter. Just how far is it from equilibrium. And so in terms of proportional reasoning, the same general logic applies. If I want to increase the energy of a spring or a rubber band or a muscle, which variable is going to give me the most bang for my buck? What's going to be most worth my time?
Your displacement.
The displacement, right? I can take a spring with a small k, but if I stretch it far enough, it can have the same amount of energy of a spring with a large k that cannot be stretched very far, right? When we think about the springs and different things, some of them are so tightly wound that it's really hard to displace it very far. So you're going to be limited with how much potential energy you can put in because you cannot stretch it very far. Are there cases where you would want a spring to not have a lot of potential? If I had low potential, what am I limiting? The eventual displacement, right? And if I don't put a lot of energy into a system, is it going to get a lot of motion out?
No.
No. Do I want my car to bounce up and down every time I hit a pebble?
No.
No, right? So I want a huge K. Pat's like, yes, I do want my car to bounce a lot. So the larger that K value, right, the less it's going to be able to stretch, so the less potential energy you're going to give it, so it can't get a lot of kinetic energy out. So your car's not going to bounce because it doesn't have the energy to do that. Instead, that energy is going to translate forward. So we can do the same thing as proportional reasoning. Again, what do we need to watch out for variable-wise? As far as if I told you that we tripled the displacement, what effect is that going to have on the potential? How much more energy I'm going to get if I stretch it 3 times further?
9.
Good, 9 because it is squared. So don't forget the squares. what we'll talk about later on in simple harmonic motion, again, springs come out in a couple of times. We'll talk about this as we get into next week as well. So it's just some things to think about. What is that relationship between the force and the displacement, right? This is work right here. Right? We talked about it in terms of the force, but work was done there. When we increase or decrease energy, we control the resulting motion, right? If I have more potential, my object can have more kinetic energy, which is going to mean it's doing what? Going faster or slower?
Faster.
Faster, right? I have to put in whatever it is I want to get out. So that's it for our notes for today. I'm going to give you your practice problems.